Good day, everyone. This is Chris with the Ancient Scholar. I'm doing this video in response to actually a couple of my students were just having just some issues wrapping their head around Newton's second law, particularly why do we call the second law the conservation of momentum, and then its common or its formal mathematical definition is that of F equals ma, and that is the force. Of course, force is a vector, acceleration is a vector. The force on an object is equivalent to the object's mass, the product of the object's mass and acceleration. And what I did is what I'm actually going to do now to kind of explain that. And basically what I did is I said, okay, well, let's start at this concept of momentum, which I will call P. We know momentum is a vector value. And we should know that P equals the product of mass and velocity. Okay? So the momentum equals an object's mass times its velocity. Obviously, we're talking about classical mechanics here. So what I did is I said, okay, well, if we want to change, if I want to change an object's momentum, I wanted to change its momentum, okay, there we go. If I want to change the object's momentum, what I'm going to have to do is I'm going to have to apply a force, okay? That change in momentum equals some sort of force. That we're going to have to apply some sort of force to the object. So let's just write this as force, okay, equals a change in momentum, delta P. Okay, so we'll start there. Force equals a change in momentum. And then I said, okay, well, fair enough. But as we know, momentum is changing with time, right? So what I did is just a little calculus. I said force equals dP dt. Okay? Now, even if you don't know calculus, that's okay. Just look at this d as a tiny, tiny, infinitesimal little change, the tiniest little change in momentum with over the tiniest little change in time. Obviously, in order to change momentum, the instantaneous tiny little change of momentum, I'm going to have to apply some sort of force, okay? Or you could just even look at these d's at this point as just a change in momentum with respect to time, okay? I need to apply force to change the momentum, and obviously time, because, you know, time is changing as well. Okay, so then I said, well, let's look at momentum here, and let's break momentum down into what is momentum. Well, momentum, P equals m mass times velocity. So what I did is I rewrote this as force equals d mv dt. Okay? The change in mass times velocity with respect to time. Mass times velocity is nothing more than momentum. Okay? So then at this point I said, hey, let's look at this concept of mass here. And does mass ever change? Again, we're talking about classical mechanics, classical objects. Well, mass never changes, so it's kind of silly to take a derivative of mass or think of mass as something that changes. So let's go ahead and rewrite this. I'm just going to erase all this here. Let's go ahead and rewrite this. So what I'll do is I'll rewrite this as the force equals, and I'm going to just put mass on the outside, m, okay, dv dt. Okay? So force equals the mass times the change in velocity with respect to time. And then I said, hey, what is a change in velocity with respect to time? What do we call that? Velocity changes, the instantaneous change in velocity with respect to time. Well, that's nothing more than acceleration, right? So A equals dv dt. Okay? So why not just simplify this even more And when we do that, lo and behold, what we get is force equals mass times acceleration. And that is how we derived, or how I derived Newton's second law of motion. We started with the concept of momentum and realized that we needed a force to change momentum, and we derived our way to F equals ma. So hopefully that little review made some sense, and as always, thanks for hanging in there, guys.